Hello, welcome to Friday morning, the end of another wonderful Chem 103 module. So today, as usual with our last day, we're just going to wrap things up. Specifically today, I want to go through the answers to some of these exercises as promised. Normally, this would be partially in preparation for a quiz, but as you saw in the announcement, I had some issues with the quiz not working, and it was too complicated to do a quick fix. So we will just postpone that off to next week, and I'll probably just have it due at the end of the next module, even though it'll be on this week's material. All right, so let's take a look at. We'll first look at the mole activity. Specifically, this end part that I said was the most important. And then we'll go back and look at the equations. If you're following along live, please ask your questions in the chat or on Discord, and I will try to address them as best I can. All right. So first, let's take a look at some of these kind of basic calculations in this mole activity. So as I said, the important thing with this is kind of understanding the idea of moles and why we do these calculations and why they're important and what it means. Not necessarily that you can do every single calculation and get them exactly right, especially as they get more complicated. So that's why I've crossed off a couple here, and we'll talk about that in a second. So the average mass of one molecule of ethanol. Remember that when we are talking about the mass of a tiny thing like a molecule, we're not going to report that in grams. We're going to report that in AMU, or atomic mass units. But we still use those same numbers from the periodic table. So we look up carbon, hydrogen, oxygen on the periodic table, and we find masses around 12, 1, and 16. I'm just going to use whole numbers to make it easier. That's fine for our purposes in this class. So I'm going to say there's 2 carbon atoms, and they weigh 12 AMU each. There are 6 hydrogen atoms, and they weigh 1 AMU each. And there's 1 oxygen atom, and that weighs 16 AMU. All right, and so the total there then would be 24 plus 6 is 30, plus 16 is 46 AMU. Actually, let me make this a little bit bigger so you can see it better. All right, so now that we've done that, it actually makes part B easier, pretty easy as well. Because remember that what we learned in this activity is that you can use the same numbers for mass of a molecule in AMU and mass of a mole of that molecule in grams. That's how that mole number was calculated. That's what it's for. So if we know the mass of a single molecule in AMU, it is the same for the mass of the moles. Now, I realize for those of you who have done significant figures calculations and things like that, I'm ignoring decimal places for now just to kind of show you how it works. But if we were being more careful, we would deal with that. All right. So another way to express this is that there are 46 grams in 1 mole of ethanol. And we can express that like an equality or a ratio. So we can say 46 grams of ethanol per, like a fraction, per 1 mole of ethanol. And so we can use that relationship for something like this. So now if we have 100 grams of ethanol, we know there's 46 grams in each mole. So how many moles is that total? As always with math story type problems, as you've been told since elementary school, it's good to just kind of think of the numbers and figure out a good estimate for what that's going to be close to. So I would say, all right, if 46 grams is about 1 mole and I have 100 grams, well, I have a little more than double, right? So my number should come out to 2 point something moles. To actually do that calculation, I'm just going to take that 100 grams and I'm going to multiply it by a factor that converts moles and grams, which is basically the reciprocal of this fraction. So 1 mole per 46 grams. So that ends up being a division problem. And if I actually do that here, I get 2.17 moles. All right. So as we estimated, a little more than 2. Now, this type of a calculation would not be on the quiz. This top one would. All right. I feel like this is a little bit of a stretch for what we need to do. If you got it, great. If not, that's okay. All right. So now let's, so this is basically the same question, number 5, same idea. If you got it, great. If not, okay. What I really want you to be able to do, as I mentioned before, is to answer these types of questions. So let's just think about moles and grams and what that means. And it's basically asking, are we counting or are we weighing? And what's the difference there? So we talked about the first one in a previous video. But let's get into it a little bit more. So 1 mole of NH3 weighs more than 1 mole of H2O. Is that true or false, and why? So to be able to do that, we need to know the masses of a mole of each of those things, which we can fairly quickly and easily calculate. Because these are true or false estimates, again, we can use whole numbers just to make things faster and easier for ourselves. So we might say, all right, NH3, I look up N, it's 14, H is 1, so NH3 is about 17 grams. And then H2O, 16 plus 1 is 18, so about 18 grams. All right, so does a mole of NH3 weigh more than a mole of H2O? No, it's the opposite, so that one's got to be false. All right, B. There are more carbon atoms in 48 grams of CO2 than in 12 grams of diamond, a form of pure carbon. So this one, the formula here is just going to be C. So now notice how the question is a little bit different here. There's clearly more mass in the carbon dioxide, 48 grams, versus 12 grams here. But that's not what the question is asking. The question is asking us to count the carbon atoms. So are there more carbon atoms in this one or in this one? And to do that, we have to convert to moles because that's how we count. All right, we've got a weight and we can turn it into a count. And what you'll see here, I think, is we don't actually have to do the full calculation. We can do the easier calculations, and then we can just figure out the answer from there. So let me show you what that means. We're going to basically do the same thing we did in part A. We want to get the overall molar mass, the mass of 1 mole for each of these compounds. So for CO2, I look up carbon is 12 and oxygen is 16. There's 2 of them, so that's 16 plus 12, which is 44 grams per mole. All right, so each mole of carbon dioxide weighs 44 grams. That's just what we did up in A also. So then for carbon, if it's just pure carbon, that is 12 grams per each mole. All right, so now we can start to think about what is really being asked in the question. So if we have 48 grams of carbon, we have a little bit more than a mole because 1 mole is 44 grams. If we have 12 carbon dioxide, if we have 12 grams of pure carbon, we have exactly 1 mole. All right, so 1 mole of carbon atoms here, a little bit more than a mole here, and each one of those has 1 carbon atom per formula unit there. So that means that this is true. There are going to be more carbon atoms in 48 grams of CO2 because that's a little bit more than a mole. All right, so if this said 43 grams, then it would be false because now we have a little bit less than a mole versus a whole mole, and the little bit less, it would be less, or fewer carbon atoms. All right, so when the question is asking us to count things, we need to be thinking about moles. When it's asking us about mass or weight, then we think about grams. All right, let's look at C. There are equal numbers of nitrogen atoms in 1 mole of NH3 and 1 mole of N2. So again, we're counting because we're being asked about equal numbers. But this time, we've got 1 mole of NH3 and 1 mole of N2. So we have the same number of both molecules. So does that make this false? Or I'm sorry, does that make this true? There's equal numbers because there's 1 mole of each? Well, not quite. And the reason why not is that N2 is going to have two N's for every molecule of N2. So if you think about the actual structures here, I'll zoom in so I have some space to draw it here. You know, NH3 is going to be an N with 3 H's. And N2 is just 2 N's. Don't worry about the fact that it's a triple bond if that bothers you. So NH3 versus NN. If we have the same number of these, let's just look at an easier number. Let's look at a dozen. If we have a dozen of these and a dozen of these, which one has more N atoms? Obviously, it's the one on the right, right? Because if you've got 12 of these, you've got 12 N's. If you've got 12 of these, you've got 24 N's because there's 2 for each. So that's the same way with moles. We can always kind of make that equivalence when we're thinking about these things. If you don't like moles, use dozens. So there's definitely going to be more nitrogen atoms in a mole of N2 than in a mole of NH3. And so this one is false. There are not equal numbers. All right, looking at D then, the number of copper atoms in 100 grams of copper, and the little s solid copper, which you maybe saw in the balancing equations worksheet, is the same as the number of copper atoms in 100 grams of copper 2 oxide, CuO. So for this one, we would say, well, same thing. We have to think about it. We've got the same mass of each, 100 grams of this and 100 grams of this, but do they have the same number of atoms? And hopefully with this one, you can see it even without doing any calculations. If you've got 100 grams of something that's pure copper and 100 grams of something that's copper and something else, there's got to be less copper in the thing that's copper and something else because that other thing is taking up some of that mass, in this case, oxygen. So oxygen is taking up some of that mass. So in this case, there's definitely going to be more copper atoms in the pure sample than in the one with oxygen atom in it, right? So that one is false. There's more copper atoms in the pure sample than in the one with oxygen. All right. And this next one's a little tricky because it sounds very similar to the one we just did, to D. The number of nickel atoms in 100 moles of nickel is the same as the number of nickel atoms in 100 moles of nickel 2 chloride, NaCl2. But in this case, because we're talking about moles instead of grams, it becomes a different question. So the number of nickel atoms in 100 moles versus 100 moles, those are both counting. So 100 moles of nickel is 100 is all pure nickel, and 100 moles of just nickel atoms. 100 moles of nickel 2 chloride, unlike the mass, the chloride isn't taking up those moles because it's counting. So each one we're counting contains a nickel and 2 chlorides. Each one we're counting contains a nickel and 2 chlorides. So that means there are 100 moles of nickel because there's 100 of these versus 100 of these. What we would have here is actually twice as many Cls, twice as many chlorides. We'd have 200 moles of chlorides. It doesn't affect the question here, but just so you know, there would be 200 moles of chlorides here. So for this one, this is true because we're counting rather than weighing. All right, and then finally, there are more hydrogen atoms in 2 moles of NH3 than in 2 moles of CH4. So again, let's think about what that means. And we can use our dozen analogy again if we want to. There's our NH3. And here's our CH4. This one's a lot like the elephants and trunks thing in that we can think about how many hydrogens per each one. So in NH3, there's 3 hydrogens per each molecule. In CH4, there's 4 hydrogens per each molecule. So in this case, there's definitely going to be more hydrogen atoms in the 2 moles of CH4. Again, think of that as dozens. If you had 2 dozen of these versus 2 dozen of these, you'd have more hydrogens in this one. You'd have 8 dozen hydrogens versus 6 dozen hydrogens, right? So this one is false. It should be the opposite. All right, so that was the mole activity. If you got these wrong, again, as with all these other worksheets, I'm not grading them closely on correctness, but I do want you to learn this stuff. So if you got them wrong, go back, watch this video, this little portion of it, as many times as you need to, look at the answers, and until you kind of convince yourself, okay, that makes sense, I think I get it. All right, let's move over to balancing equations. We looked at some strategies for balancing equations in a previous video, so if you want more instruction with that, go ahead and watch that one. In this case, I'm going to use pretty much the same technique that I went over in that video, but rather than explicitly list out each atom, I'm going to try to just do it directly. So I'm going to say, all right, Cr and S8. I can see I've got one Cr here and two here. So I might put a 2 there, but then I also can notice that the S's are a lot weirder here. I've got 8 and 3, so I've got to find a common multiple for those two, which is 24, right? Is the lowest common multiple of 8 and 3, because 16 is not divisible by 3. So 24, I got to get 24 S's on both sides. And to do that, I just flip those numbers. So 3 S8s and 8 S3s is going to give me 24 on each side. So that leaves the chromium one. 8 times 2 is 16. So I need 16 on this side. Not too bad. All right, next one. Similar idea. I can see that my oxygens are out of balance. I can see that my carbons are in balance and iron is out of balance. Now in this one, I want to start with balancing the iron because oxygen is in everything. So it's going to be very difficult to figure out how that should get balanced in a way that works. And in this one, it actually kind of works anyway, works out anyway, but in other ones, it may not. So I really want to leave that for last because there are so many choices there. And I know I've got 3 irons on the left and 1 on the right, so I got to put a 3 there. No question there. And then if I add this up, I've got 5 oxygens on the right, 5 oxygens on the left, so I'm done. So that's it. And then the last one, this methane combustion. Again, I'm going to save my oxygen to the end because already I can see it might get a little weird, but I got 4 hydrogens on the left and 2 on the right. I can put a 2 here and then end up balancing those. And then I've got 4 oxygens on the right, so I need a 2 here to balance those out. And then the next questions deal with kind of using moles. So the reason that we have to balance these equations, besides just the conservation of mass, but the practical reason doing this in the lab is you have to figure out how many or how much of each quantity you need if you want to mix it and make a efficient reaction. So those numbers actually, as you saw in this lesson, end up also meaning moles. We can talk about them as individual molecules, but we can also talk about them as moles. So let's look at question 2. For each mole of S8 molecules consumed in the reaction in exercise 1, how many moles of Cr2S3 molecules are produced? So for each of these, how many of these are produced? Well, it's a little bit of a tricky question because the ratio is 3 to 8. So for every 3 of these, we produce 8 products. So for every one of these, how many of these do we produce? Well, we just got to divide each of those by 3. So we get 8/3 of a mole, which we could also call that 2 2/3, or whoops, that's not 2/23s. 2 2/3 or 2.67, whatever you want to call that, is what you would get if you divide 8 by 3. All right, and then we've got a balanced equation here. And we can look at the same basic question. How many moles can be produced by 4 COs and 2 Os? So 4 COs would be double, right? And then double again. So we have still the right ratio. We've just doubled each. So we're going to get double the product. We're going to get 4 moles of CO2. And then we can convert that to grams. using the techniques from the other lessons. So for C is 12, O is 16. So if we add that all up, we get about 44 grams per mole. And we can multiply that by 4 moles. And whatever that is, 176. I think that's right. I'm not sure. Okay. And then you can draw some pictures of how that would work. So in this case, reaction 1 in the model is way up here. H, that's this one here. So let's draw some pictures for that. So it'd be 2 H2s plus O2. So I need 2 of these. And then 1 O2, we'll call that O2. And then I end up with 2 H2Os. The reason for this activity or this exercise is just that it really, I think, emphasizes why we need to balance things when you can see the pictures and you can see that every single dot has to have a dot with it in the products also. Right? So that's how I would do that way. And you can do a similar thing here. All right. So hopefully that stuff went okay for you. We'll have a quiz to practice next week. Next week, we'll start our next module, which will focus on greenhouse gases and climate change and infrared light. And there's light in general, and there will be a neat experiment using your kit, using the UV active beads. So something to look forward to for the next module. And, we're getting close to the end here. A couple modules to go. And then that's it. So only about 6 weeks left, I think, of class, if I'm counting that right. 5 or 6 weeks before exams. So what that means, most importantly, is get your assignments in. If you still have outstanding stuff from before, you need to get that stuff in. The withdrawal date is coming up, and you don't want to leave those assignments not done as we get closer to the end and you don't have the option to get out without a grade reported. So if you have stuff that you haven't turned in yet, you can still do that. Turn it in. Let me know you've turned it in, and you can still get credit for it. Otherwise, we'll keep moving forward. Let me know if you're having any issues or if there's anything you don't understand. And if you're celebrating holidays this weekend, have good holidays. If not, just enjoy the beautiful weather. And I will see you Monday evening to introduce the next module. Thanks, everybody. Bye.